All right, guys, hopefully I had a little break. Let's keep going now with our strong and weak bases. This will be the final podcast of week number 10. Ultimately, if you think back to the data booklet on page 8 and on page 9, you'll notice, of course, that we've got a whole lot of Ka on here, right? There's K at the top. When I switch to this page over here, this is a continuation of Ka going down. And if you continue flipping through your data booklet, at no point do you find a list of Kb. So it's kind of a like, oh, well, why isn't Kb there? Obviously, the base ionization constant is a thing. Why don't we have a list of them? Reason why is that we can derive Kb from Ka, also using Kw. Now, in terms of the derivation of this, guys, that's something I go through in class, and I'm not going to do it through distance learning, but if it interests you, by all means, look it up. It's a fairly logical derivation, but it's always interesting to see where formulas come from. So check it out if you're curious, by all means, all right? But ultimately, here is another new formula that you need to know. So once again, I think in this 1 week alone, there have been a massive number of formulas with all of the different pH, pOH, etc. ones that have come your way. So please write this one down, have it in your head, because it's going to be essential for you to figure out. Now, just to remind you, Kw you can find on page 3 of your data booklet, and the Ka values that you need, you're going to be able to find on pages 8 and 9 of your data booklet. So that's where you look for both of those. Now, let's do a really simplistic question just to get you used to these. I want you to calculate the base ionization constant, so Kb, for both the propanoate ion and for the benzoate ion. Which base is stronger? Now, here's the deal, guys. You can approach this in 2 different ways. One way that you can do it is you can look at, okay, if this is propanoate, that would go with propanoic acid. It's not the same as, but if you put a hydrogen on it, it's propanoic acid. Similarly, you can think, okay, if this is benzoate, it would be, when you add on a hydrogen to it, benzoic acid. Knowing those 2 things, you can go over here and start to look at the table. Now, this is what I mean that there's another way to look at it. So if you understood that, yeah, you can find your propanoic acid good to go. Alternatively, you can look for the propanoate ion, right? So here's the ion. Now, list-wise, that is actually the base formula, right? The conjugate base formula. That word conjugate is one I'll explain to you more next week. But this base is associated with this acid, and the Ka for that acid is that 1.3. That is the one that we need. So in terms of how I would just write this out for an understanding perspective, like, okay, I know Kw. Kw is on your data booklet, it's 1.0 times 10 to the negative 14. The associated Ka is 1.3 times 10 to the negative 5. That's what I just got from page 9. And take note for yourself, this is for propanoic acid. Right? That's why I'm using it. It's associated with the propanoate ion for propanoic acid. Now we can start to number crunch. Kb is equal to Kw over Ka. 1.0 times 10 to the negative 14, none of these have any sort of units, over 1.3 times 10 to the negative 5. You can see we're going to have 2 sig digs when all is said and done. Kb is equal to 7.7 times 10 to the negative 10. There we go. Propanoic acid, done, ready to go. Let's do a similar process for the benzoate. Now, benzoate, we always use Kw to be the same. 1.0 times 10 to the negative 14. That's not going to change. Now, Ka is going to be for benzoic acid associated with the benzoate ion. So that, I'll use the turquoise one for this. Here's benzoic acid associated with the benzoate ion. In other words, this is the Ka that we need to pull from. So there we go. Ka for benzoic acid then is 6.3 times 10 to the negative 5. They are related. Kb is equal to Kw over the Ka of the corresponding acid, the benzoic acid. So 1.0 times 10 to the negative 14 divided by 6.3 times 10 to the negative 5. And Kb is officially equal to, remember, 2 sig digs, 6.3 times 10 to the negative 10. Now, back to the question, it said, which is the stronger base? Well, ultimately, guys, the one with the stronger base ionization constant, with the higher, I should say, base ionization constant, is going to be stronger because it means it ionizes a little bit better. It's going to favor the products a little bit more. If it favors the products, we will have slightly more hydroxide, thus making a stronger base. And in this scenario, this number for the propanate ion is slightly higher. Therefore, there is my stronger base. Okay, so now the next few problems are simply going to be the same process that you've done already, but added into that this new formula of how to calculate a Kb. Let's check it out. First things first, as per usual, guys, see what you've got. And looking at this, you might go, wow, I don't know what that is. And you should memorize it. This is ammonia, folks. It was introduced to you in Chem 20. Ammonia is, by the nature of what it is, a weak base. And it still ionizes by gaining a proton from water. So, reacts with water. The hydrogen, just one of them, is going to switch over. Equilibrium arrows. If you add an extra hydrogen on there, there's no longer 3 hydrogens, there's now 4. The NH3, the ammonia, had a net charge of 0. We're taking 0 and adding a positive 1. That's a +1 charge. So ammonium has a positive 1 charge. Ammonium ion, and we're going to have, of course, hydroxide. There you have it. Okay, let's start go through this process then. This is an equilibrium scenario, so we're going to have to analyze it from an initial, a changing, and then the equilibrium concentration. It begins with a 0.10 mole per liter. Now, from there, we're going to subtract some amount. The ammonium ion starts at a 0 mole per liter, as does the hydroxide. Both of these are going to go up by an X value. Water doesn't have a concentration, it's a pure liquid. 0 plus X is simply X, Now this is similar to what we saw with the weak acids. 0.10 minus X, that X value is so teeny tiny that we assume the concentration, the initial concentration of the weak base will be the same as the equilibrium concentration of the weak base. So we just take it as 0.10. Okay, here's the extra step. Before, with acids that were weak, we would just go find the Ka and go for it. This one's different. We don't have a list of Kb, so we need to calculate it. Kb is going to be equal to Kw over Ka. You are going to take the Ka value for ammonium. Not ammonia, but ammonium. Hint, hint, guys, it'll always be what is produced with hydroxide. So in other words, you're going to go to your Chem 30 data booklet and start doing a hunt. If your brain understands the ammonium, great. But if you need to look for the formula, then no problem. Or you can look for the base formula if that makes it easier for you. And there you have it. There is your Ka associated with the conjugate acid of the ammonia base. Okay. So that's just going to start to get plugged in here. Kw 1.0 times 10 to the negative 14. And our Ka from the data booklet, 5.6 times 10 to the negative 10. Number crunch away, don't round though. Kb is equal to 1.7857 ... times 10 to the negative 5. Now, why is this useful? Well, because once we have the equilibrium law for this equilibrium system, I can then solve for my unknown, x. I could do so algebraically. So let's get that equilibrium law. Kb is equal to the concentration of the ammonium times the concentration of hydroxide over the concentration of ammonia. Plug in what you know. Kb we just found. It's 1.7857 ... times 10 to the negative 5 equal to ammonium and hydroxide are both x, which is equivalent to x squared. And we can just use 0.10 because we assume that they are close enough. We can use the same number for the initial equilibrium of that ammonia and H3 and the equilibrium concentration. Okay, here we go. Rearrange. X is going to be equal to the square root of 0.10 times 1.7857 ... times 10 to the negative 5. In the end, we get X, which is hydroxide concentration, equal to 0.001336, don't round it, moles per liter. Whew! Lots of work, right? But we're not done. What do you know? The whole goal of the question is to find pH. Guys, you can't get pH directly from hydroxide, right? It doesn't work that way. So we're going to have to do a conversion here. The only way to get pH is from hydronium concentration, or by playing around with the knowledge that 14 minus POH will give us pH. Lots of different routes. You decide how you want to do it. I'm going to do it this way for this question. I'm going to find the POH first. Your call how you go about this, guys. Negative log times the hydroxide concentration that we just found. Negative log times 0.001336 ... moles per liter. Okay, there we go. Number crunch. Don't round yet though. POH is equal to 2.874 ... I get to use what I think is one of the easiest equations, that pH is equal to 14.00 minus the POH. Again, all unrounded values at this point. 14.00 minus 2.874 ... and 2 sig digs, 11.13 is my pH. The 1 and 3 at the end are significant. There we have it. Guys, process-wise, this question is identical to what we were doing with the other weak bases and with the other weak acids. There's no difference. It's just that you're going about it in a slightly different way. The next question here with the nitrite. This one again, identical process, no difference whatsoever. So please have a look at it. The full answer is given to you on the notes. You end up with a pH equal to 8.13. Look at it, guys. Try it out. See if you can get these. Are they potentially a little bit difficult? Only because there is a lot of process, which means there's lots of spots for error. So take your time, be thorough, double check your number crunching, and you'll be in pretty good shape. This one as well, we've done a very, very similar question again, right? It's just that you're going to have to find your KB and then do rearranging in order to find it. I'll do this one with you, just because it's got a little bit of a twist from what we've done before. So we're wondering, this weak acid, HCOO negative, will cause a pH of 8.35. Okay, weak base for sure. So here we go. HCOO negative aqueous is going to react with water, H2O liquid. The water is going to transfer a proton over. We are going to end up with formic acid, HCOOH aqueous, plus that hydroxide ion, aqueous. Weak acid, which means we have our equilibrium situation. So let's draw those concentrations for initial changing in equilibrium. And the whole point of the question, the whole goal is to find the initial concentration of this HCOO negative. Now that's what this is asking, right? So we need to work backwards to look for that. How are we going to do this? Well, let's just start going through the process. All that we know in this question so far is the pH. That's all we've got. Now, how is that useful? Well, as long as you've got pH, you can easily get pOH. 14.00 minus the pH is 14.00 minus 8.35. We now know that we have a pOH of 5.65. And that's super useful. As soon as you have the pOH, you can get the hydroxide concentration. And it's going to be the hydroxide concentration at equilibrium. So I now have the means to get this number. Okay, let's go through it. Hydroxide concentration is going to be equal to 10 times to the exponent of the negative pOH. In other words, 10 to the exponent of negative 5.65. Thus, hydroxide concentration is 2.2387, don't round, times 10 to the negative 6 moles per liter. Okay, this is a huge thing that was just found. By knowing this number, what you have just managed is to get not only the concentration at equilibrium of hydroxide. So let's write that in. Yes, you got that. 2.23, keeps going, times 10 to the negative 6 moles per liter. Sure, we got that. But because we know that we have hydroxide starting at 0 moles plus X, which ends up being plus the 2.23, right? 2.23. And we had the formic acid also plus that 2.23, which means it's going to have an identical concentration, 2.23 times 10 to the negative 6, moles per liter, right? They're same. And what that also means is that this original one, if I count this as an unknown as X, if I subtracted that same 2.2387 times 10 to the negative 6 moles per liter, I now have an equation for the equilibrium concentration. Oh, that potentially is useful. X minus 2.2387 times 10 to the negative 6 moles per liter. Okay, not an answer yet, right? We're not there, but something potentially useful still. Let's continue. At this point, an equilibrium law is not that helpful because I don't know Kb. Do we have a method to find Kb? Absolutely. Kb is equal to Kw over Ka equals 1.00 times, 1.0, not 00. There we go. Times 10 to the negative 14. Now, for that HCOO, if we go over here into the data booklet and keep on looking for it, you can find this right here, right? So there's that HCOO negative base. It's associated with formic acid, so I need to take the Ka associated with it, right? That's not Kb, that's Ka. But that's the number I'm going to write down. So 1.8 times 10 to the negative 4. Number crunch away, you're going to end up with Kb equal to 5.5 repeating times 10 to the negative 11. Whew, we're getting there, guys. Ultimately, we now have only one unknown. Think about this. We know the equilibrium concentration of hydroxide. We know the equilibrium concentration of HCOOH. We know Kb that can go with the equilibrium law. What we don't know is the equilibrium concentration of HCOO negative. But we can find it. It's our only unknown. So algebraically, this just became super doable. Let's make the law. Kb equals HCOOH times by the concentration of hydroxide divided by, and here's partly what will help us, HCOO negative. Now remember, this is the concentration at equilibrium, so it's not our end answer, but it'll get us close. Rearrange this thing. We need to rearrange it in order to get this by itself, right? So play around with it algebraically. We end up with, in the end, HCOO negative equal to the formic acid, HCOOH, times the hydroxide, OH negative, divided by the Kb. Now we can start plugging in numbers. Equilibrium concentrations of the top ones, 2.2387 ... times 10 to the negative 6 moles per liter. They're both the same, so I can simply square it. Divided by the Kb that we just found. So divided by 5.5 repeating times 10 to the negative 11. Number crunch, number crunch, number crunch. You end up with the equilibrium concentration equal to 0.090213 ... moles per liter. Well, guys, that value there is equal to this one, right? So that means to get x by itself, I simply need to take this and add, yay, we're so close, plus 2.2387 ... times 10 to the negative 6 moles per liter. Lo and behold, we have now just figured out the initial concentration of the HCOO negative aqueous initial is equal to, we need 2 sig digs, 0.090 moles per liter. Dun, 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 and there it is. A little bit of a trickier question, definitely a little bit of a twist on it. All of that is written on the PDF of the notes, so you can have a look at it there. Listen to the podcast again if it helps you. Guys, we are officially done the podcast of this week. Yay! And you can do the rest of the homework assignment, 8 all, 9, 10, and 11. Done and done. Take some time to work through it. This isn't a quick one, but it's a goodie. Have a great weekend. Talk to y'all soon.